One of the weirdest developments from physics in the 20th century, late 19th century, is radioactivity, which is a process where elements change their identity into other elements. This is what alchemists were trying to do hundreds of years before when they were trying to find a way to change lead into gold. And of course, that's impossible in chemistry because chemistry just involves shuffling electrons around, but the identity of the element, it depends on the number of protons in its nucleus. So chemistry doesn't have anything to do with that. But this was a big discovery, and the early scientists involved were Becquerel and Marie and Pierre Curie. They all won Nobels, and Marie won two of them, and almost nobody has done that. Uh, the important sort of questions that had to be asked after this was discovered was why do only some elements change, and what kind of energy is coming out of these elements when they change. And if we want to understand this, we have to learn about all the forces in the nucleus. There are really four of them. Uh, First, we have the electromagnetic force. We spent the whole semester studying that, and that's just the Coulomb repulsion of all the protons on all the other protons in the nucleus. There's got to be something else, though, because that force would be enough to blow the nucleus apart, and it obviously doesn't happen that way. Uh, as people continued to investigate the nucleus, they realized that there were neutral particles in there, almost the same size as the proton, just a little bit larger, but with no electrical charge. Both neutrons and protons feel what's called the strong nuclear force. This force is attractive and a bit more than 100 times as strong as electromagnetism. The reason you haven't seen it pop up in physics class yet is its range is only about 10 to the minus 15 meters. That's about the size of a proton. So that means this is a force that's exerted from one neighbor to another, pretty much. The range of electromagnetism, on the other hand, is infinite. So we can feel that at our scales. In every nucleus, except of course hydrogen, which just has the one proton, there's got to be a balance between the protons trying to blow the nucleus apart because of electromagnetic repulsion and the strong force trying to hold it all together. When we're talking about small nuclei, generally a 50-50 mix of neutrons and protons will make a stable nucleus. If you look at helium, two protons, two neutrons, we could write that with a little superscript 4, where 4 tells you the total number of neutrons and protons, and knowing that it's helium tells you the number of protons by themselves. The most stable form of carbon is carbon 12. That has 6 neutrons, 6 protons. Sulfur has 16 of each, so 32s would be our common form. Uh, but as we keep stacking these particles together, building larger and larger nuclei, the repulsion of every proton acting on every other proton starts to overwhelm the strong force, and we need more sort of spacers in there, like the neutrons, to keep the nucleus stable. Remember, they provide the strong force, they don't feel the electromagnetic force, so putting them in there can counteract that tendency for the infinite range electromagnetic force to blow everything apart. By the time we get up to something fairly heavy like gold, that's 197 AU. Gold has 79 protons, and that means 197 AU would have 197 minus 79, or 118 neutrons. So instead of 50-50, now we're at about 3 to 2 neutrons to protons. Even with this modification, it can't go on forever. And we find that polonium 210, which has 84 protons and 126 neutrons, will decay fairly quickly. It'll turn into something else. If we add or subtract neutrons, we can get more or less stable isotopes of materials. Isotope means same number of protons. So 209 or polonium 209 and polonium 210 both have 84 protons, but the number of neutrons drops down to 125 for polonium 209. So those are isotopes of polonium. In general, there are three types of radiation we're concerned about when these elements change. Nobody understood what they were in the early 20th century, so they just started labeling them with letters from the Greek alphabet, alpha, beta, and gamma. People found that alpha and beta particles got deflected by magnetic fields in opposite directions, and we know that moving particles are deflected based on their charge, so they must have opposite charges. Gammas didn't get deflected at all, so they must not have carried any charge. By looking at the products more carefully, people discovered that alpha particles are really just a group of two protons and two electrons, in other words, the nucleus of a helium atom. Beta particles are just electrons, and gamma rays are just very high energy photons. Uh, One of the things that's important here when we look at how dangerous are these things, because people freak out about radioactivity, a lot of times unnecessarily, uh, it depends on the energy of the decay. A lot of energies in atomic reactions, which are chemistry, are on the scale of electron volts. We talked about this when we looked at ionizing versus non ionizing radiation. Nuclear energies, on the other hand, are typically more like millions of electron volts. Even if we had alpha, beta, and gamma particles that had the same energy, there are other things that distinguish them, and that's their charges and their mass. The alpha particles are about as massive as 8,000 electrons. So if we have an alpha with 5 MeV of kinetic energy, we can find its speed using the Newtonian physics. We'll try this first and see if we're allowed to do this or if we need relativity. We put in Newtonian physics and solve it just like it's a baseball or something. And we get a speed of 1.55 times 10 to the 7 meters per second, which is about 5% of the speed of light. So that's ridiculously fast, but still well below where we really need relativity. So we don't have to redo this. We can get away with this for the alphas. On the other hand, for electrons, since the rest energy of an electron is only 0.5 MeV, this is definitely going to be a relativistic case. So if the kinetic energy is 5 MeV, we plug this into our formula from the relativity chapter, where we know mc squared is 0.5 MeV for electrons. So we get that gamma minus 1 is 10, so gamma is 11. We solve for V over C, and we get 99.6% of the speed of light. So the electron that has the same energy as the alpha particle is moving much, much faster, and it's, of course, harder to stop. The alpha particle also has a charge of plus 2e, so it's more likely to interact with matter. What this means is alpha particles are usually very short range, and almost anything will stop them. As long as it's outside of your body, you don't have to worry about alpha particles because the dead skin cells on your body will do it. Even smoke in the air will stop alpha particles, and that's how your smoke detector works. Or a piece of paper would give you good enough shielding. For beta particles, it depends on the energy, but it could take several millimeters of metal or centimeters of wood or tens of centimeters of your body. And gamma rays of this energy can go through even a few centimeters of lead. Lead's usually used when you talk about shielding because it's high atomic number, so there's lots and lots of electrons densely packed together to try and stop these particles.